today in the Landau-Ginzburg seminar, we're talking about matrix factorizations. And matrix factorizations are important because they will form the one morphisms in our bicategory of Landau-Ginzburg models when we get around to defining that. So for the duration of this talk, let S be a commutative ring. And F an element in S. And the example to keep in mind is when S is a polynomial ring over some commutative ring K. So taking K equal to C or K equal to the real numbers is fine, possibly in more than one variable. Concretely, I think the most concrete way to think about matrix factorizations is as a pair of matrices P and Q, say pair of n by n matrices P and Q, which satisfy this equation here, where I is the appropriately sized identity matrix. And so, for example, if say S is, I'll switch color. If S is this polynomial ring, then we can take P equal to X, Y, X, and Q equal to X minus Y, X. And that's going to be a matrix factorization of F, right? Now, we can sort of upgrade this viewpoint a bit if we think F? About... what's that, sorry?
What's F?
So F is an element in...
Yeah,
sorry. Yeah, good point. Yeah. Sorry.
I guess we can figure it out. But
yeah, and F is this difference of squares. So that's the same example I think you were talking about, Dan, in maybe the first or the second talk when we started talking about LG. Yeah, so D square to F times the identity matrix. Okay, so we can upgrade this point of view by thinking about these, by choosing generators for say these are n by n matrices. We can choose generators for S n copies of S, and we can associate to P and Q morphisms from Sn to itself. And then with this view, we can think about the matrix factorization. We can express the data of this matrix factorization like so. And right now we can view this as a Z2 graded S module, right, where we have this part in degree 0, this part in degree 1, and this part is the same as the first part. It is also in degree 0, so you can sort of identify this end and this end. And together with an odd endomorphism, which is made up of P and Q here. So with an odd endomorphism given by, let me get this the right way around, this, yeah, right? So there's some immediate generalizations we can make to this, right? So what if we allow matrix factorizations to be of kind of infinite rank, so of maybe countably many copies of S appearing here or more? Or more generally, what if we allow these graded parts of the matrix factorization to not be free S modules, so just any old S modules? So that's what we're going to do, and that's what we'll define on the next board. Do I need to move actually to line the camera up?
I think the first two boards are in view, and then you can move over to get the other two when you need to. But for the moment, it looks good.
Okay, cool. Okay, so yeah, so we'll move to the definition. So a linear factorization is a of of f in S is Z2 graded S module X together with an odd map such that d squared is equal to f times the identity on X, right? A matrix factorization is a linear factorization, which I write for LF, is a linear factorization in which X is free over S. And we say, and matrix factorization is finite rank if the underlying module is finitely generated. So if X is finitely generated. Okay, are there any questions with what we've got so far? Okay, cool. Okay, so depending on what maths you've seen so far, you may or may not know that a complex of S. We've also got this idea of a complex of S modules, right? So we can think about a complex of S modules as a Z-graded, so complex, right? As a Z-graded S module C together with a differential which squares to 0. And a linear factorization can kind of be viewed as a Z2 graded cousin of a complex of S modules, although in many respects they're less interesting because there's no notion of cohomology for linear factorizations. But nevertheless, like many of the concepts that we use for complexes just readily extend to linear factorizations. So, for example, we can define a morphism of linear factorizations in the obvious way, which we'll do now. So, a morphism of S modules. Oh, sorry. So we'll say that this is a morphism of S modules. Oops, S modules. Oh, no. A morphism of linear factorizations of F. I've sort of phrased this in a bit of a weird way, but we say if it consists of an S linear map between these modules, such that it commutes with this differential in each case, meaning that the diagram, which I'll try and squeeze in here, so I should say an even degree 0 linear map. Which commutes, so that both squares in this diagram commute. Okay. If there's no questions, we'll move on to talking a little bit about the geometric content of matrix factorizations. Okay. Okay, so Now we're going to introduce. Hold on. So now we're going to introduce a new ring R, which is going to be S mod the ideal generated by F, and we're going to be talking about matrix factorizations of this element F in S. And now I'm going to explain how to associate a geometric object to a finite rank matrix factorization XD of F. In the case that F is not a zero divisor. Okay, so when S is a polynomial ring, this geometric object is going to be the zero set of S, right? So for S equals to, say, K AM, then it's going to be a part of the zero set of F, right? So it's going to be something, something inside this thing. Right. So we'll be focusing on the case when S is a polynomial ring, and also just note in the case that that say K is C or R, that F being not a zero divisor just means that F is non-zero. Okay, so the first step is to associate to our matrix factorization a particular type of R module. Now, so we'll just introduce some notation. So the components of our matrix factorization look like this, right? So we'll use this to denote the degree 1 and degree 0 components, and this to denote the two maps. Now, since we have that D0, D1 is F, X1, we know, and F is not a zero divisor, we know that D0 is monomorphism. Right, and the same can also be said of D1, although that's not relevant. And that means that we end up with a short exact sequence, which I'll write down now. So this is going to be, let's say this is S to the N. This is S to the N as well. Which is finished by the co-kernel of D0. And we'll call this co-kernel the module M, right? And we can note that F acts trivially on M, right? So if we take M, which is equal to the image of some element of this thing here in M, then Fm, well, that's just because F is just an element of the ring, that's Fs, right? But then this differential squares to F, so we can write this as E D0 D1 of S, and well, the sequence is exact, so we end up with that being 0, right? So the point being, right, is that this module here is, oops. Oh, that's not. So this is actually an R module. Right. Okay, and I'll move over to the next board. Were there any questions at the end of this one? Okay. So the R modules which arise in this way are special. So we'll let K of R denote the category, the subcategory of R modules, which can be put into short exact sequences of the form of this form here. So where we have, two free, this short exact sequence of S modules. So we're calling this category. And when S is a regular local ring, then this is the category of what are called Cohen-Macaulay modules. But that's not how Cohen-Macaulay modules are usually defined. And this is the context in which matrix factorizations were sort of first introduced by Eisenbart. And I've got some.
Can I just ask a question?
Yeah.
Sorry to interrupt you. I'm just one board behind you. So what was the significance of the fact that F annihilates the module M? I think I missed that.
So it means that M is a R module rather than an S module. So we have this sequence of S modules. Yeah.
Yeah, got it. Thanks.
Cool.
I was trying to understand the calculation, but then I didn't understand the point of it. But that makes sense.
Oh yeah, sure, no worries. Cool. Okay, so so I think all I was really saying here is that, well, this is a special category of R modules, and with certain conditions on S, we get a different, some R modules called Cohen-Macaulay modules, which are sort of significant for reasons I don't understand outside of the world of matrix factorizations. But yeah, this thing will come up again later. Okay, but now I want to move on and talk about, when we have when we get our module from the matrix factorization, to then take that to an algebraic set. And we're going to be doing this in the case that S is KX1 is a polynomial ring over a commutative ring, right? So we've got X, D here, and from that we've obtained M and R module. Okay, so recall the definition of the annihilator of an S module. So I'll write that down. So it's an ideal of S, right? And we denote it like so. And it's the subset, or the ideal of S, consisting of all the elements which annihilate the module. Right. So for example, the annihilator of the S module R, right? So remember, R is S mod the ideal generated by F. Well, that just gives you the ideal F back again. Okay, so for our module M, we know that it's an R module, right? So that means that we have the inclusion of ideals F contained in the annihilator of M, right? And then that means that when we look at the vanishing set of each of these ideals, we get the following inclusion, right? So we can apply this thing, and we end up associated to this annihilator a vanishing an algebraic set contained in the algebraic set associated to this polynomial F, right? And this is also called the support of M. Okay, so yeah, and if we assume, say K is Noetherian, so for example, if K is the complex numbers or the real numbers, then this will be the vanishing set of finitely many polynomials. Okay, so yeah. So in summary, what we've done is we've associated, we've gone from, I sort of wanted to draw that up there. we've gone from a matrix factorization, or sorry, a finite dimensional matrix factorization of F to an R module in this category of R modules KR. And then to that, we've associated an algebraic subset. Let me erase this. An algebraic subset called the support of M, which is contained in the vanishing set of F, right? Okay, so we now might move on and talk about some examples and some practical, doing this calculation for particular matrix factorizations. But were there any questions first before we go on to that?
Yeah, sorry, just remind me where you actually used that the matrix factorization was finite dimensional for this.
Yeah, good point. I suppose we didn't, and the reason I didn't think about extending it is because you can show that a category of matrix factorizations where you choose some morphisms differently, you can show that that's equivalent to this category here. So I guess that the
partly the answer is the relation between the annihilator and the geometry is not precise in the case of an infinitely generated module. So if you took M to not be, if you have a finitely generated module over an Noetherian ring, for example, the associated primes of the annihilator correspond to so one understands how to think about the primary decomposition of the annihilator and what the primes that correspond to that mean. But in the case of M infinitely generated, well, the annihilator is an ideal in a Noetherian ring, so it's always finitely generated. But for instance, you might the primes the associated primes of that ideal will be the primes that appear in the decomposition series of M if M is finitely generated. But if N is infinitely generated, so you assemble it with a bunch of exact sequences with infinitely many primes, then I guess some of those primes must be missing from the primary decomposition of the annihilator, because that's a finitely generated ideal, so it has finitely many associated primes. So there's more geometry in the module in that case than there is in the annihilator, so you've lost information, which you're doing anyway in this case, but it's one reason to stick to
Yeah, okay. I kind of had the question earlier as well, which is why we care so much about the finite rank case anyway. I mean, I don't really see why we move from linear factorizations to matrix factorizations. Is the answer to that buried in what you just said?
I think it's visible at the level of what we're discussing here, which is still so abstract that it doesn't seem to make any difference. But a short answer is that if you take the homotopy category of arbitrary matrix factorization, so infinite rank allowed, then that category is generated in the sense of it's the smallest coproduct. It's the smallest triangulated subcategory of itself closed under coproducts, which contains the finite rank matrix factorizations. So the finite rank ones generate everything. So there's really no...
Oh, I see.
You add colimits, but it's a bit like the relationship between finitely generated modules and all modules. You do care about modules that aren't finitely generated, but from some point of view, all the information is already in the finite ones.
Cool, thank you.
Are there any other questions? Okay, cool. Let's talk about some examples. We'll go back to the first board. Okay, so an easy first example is the following matrix factorization. Oh, sorry, I should say. So let S be this polynomial ring. So polynomial ring in two variables over the real numbers, and we'll use our example the same example here that we had before.
Sorry to interrupt, Rohan.
Yep.
Maybe you erase that board manually with the eraser.
Yep.
If you could clear the boards in future, because when they're cleared, they get saved. In case.
Oh, okay. Sorry about
unless you no, don't apologize. I should have mentioned unless you want it to not be saved, but that's
Sure.
that's up to you.
Yeah. All right. Cool. Okay. So let's look at this simple matrix factorization. Okay, where the first map is just, well, it's just F again, and the second map is 1, right? So we take the co-kernel of the first map, and we get the module x, y, modulo x squared minus y. So this is the module R that we were talking about before. The annihilator is, well, it's just this thing. And then the algebraic set is, well, it's going to be everything, right? We end up with just the vanishing set of F. Okay, so that's good. On the other hand, if we say we take say we swap these around, right? So say we put 1 here, and we put x squared minus y squared here. Well, then the co-kernel of this thing is just going to be of this thing here is going to be 0 module, which is annihilated by so the annihilator is Rxy in this case. And then that gives us the algebraic subset, just the point 0. Right. Okay. Cool. All right. So maybe now let's look at something that isn't nothing or everything. So another matrix factorization. Oops, xy. So in this case, well, again, we end up with the co-kernel of this is just, we end up with the module R xy modding out by x plus y, right? And then again, the annihilator is, well, it's just this ideal here. And then we end up with the algebraic subset v x plus y, right? So so the vanishing set of F looks like this, right? And then in this case, we've gotten just this part of it here, right? And then the last example I want to talk about is actually one I didn't figure out the answer to. And it's the example from the start of what we had before, right? On the my first example of the matrix factorization. So it's x, y, y, x, and then x minus y, x. And then, so in this case, the module that we're associating to it is, it's this thing modded out by the image. So it's the ideal of all things of the form ax plus by, bx plus ay. So So as A and B
Do you
vary
have
in...
squares on all of your polynomial rings now?
Yep. Thank you.
Nice.
And yeah, basically, I haven't really been able to figure out the annihilator of this module yet. So maybe, I don't know. Yeah, I guess I don't have too much more to say in this, but in theory, this annihilator exists, and you can look at the zero set.
The passive-aggressive way to say that is exercise for the audience.
Yeah, I didn't want to say that because I feel like you would have called me out for it.
Yes,
the only
yes,
reason I've mentioned it is because I thought you would have called me out for not mentioning it.
I want to just naively ask, isn't answering a question like that kind of the role of a regular sequence? Can't you reduce that question down to the question whether these two polynomials are regular sequences, or is that nonsense?
Well, then,
I don't know.
I was thinking earlier, when we have the general theory of linear factorizations, it seems like the canonical example of a module S that you might be interested in where it does have zero divisors would be in the case of a polynomial ring modded out by a polynomial, right? So I kind of had in my head whilst you've been talking that you want to iterate this process. So you start with a polynomial ring, and then you consider a particular polynomial f. But then once you've drawn your conclusion on that, you mod out by that, the ideal generated by that polynomial, and then you repeat the process for the next polynomial that you have in your sequence. So I thought there was kind of regular sequences lurking in the background here, but maybe that's not the correct intuition to have or something.
I don't think so. Sorry to be blunt, but I think that's... I mean, you could consider... you can consider multiple polynomials, right?
Mm-hmm.
That would be something different to a matrix factorization, but you can consider an analog of matrix factorizations for instead of hypersurfaces, things of codimension 2. So you'd have a regular sequence of length 2, and geometrically you can talk about Cohen-Macaulay modules for that and ask what the analog. But somehow you really, at that point, it seems more convenient to talk in the language of Cohen-Macaulay modules than matrix factorizations, where there is a kind of theory of iterated matrix factorizations or so on, but that's not very well developed, and I guess not super relevant here. I think, Rohan, partly it's confusing the way you wrote that quotient, right? I mean, that's you make it look like you're modding out by an ideal or something. You mean, you mean the span of two column vectors.
Yep. Yeah. Sorry. This is a submodule.
There's like a transpose in there that's missing and makes it look like an ideal.
Yep.
Yes, that's actually A times the column vector xy plus B times the column vector yx.
Cool. Were there any other questions? Otherwise, I'll move on from the examples. Okay, cool. I'll go take a look at the next board. Confirm clear. There we go. Okay, so I thought when I was preparing this talk, okay, so what about algebraic sets to matrix factorizations? Like, can we do that? And I guess no is the short answer. At least I don't understand how to. So say we're given an algebraic set VI, where I is an ideal contained in oh, sorry, this should go the other way, right? Where I is an ideal containing F. Can we associate this to a module in a module in this category I talked about before, which is when S is regular local, the category of co-Macaulay modules. So it's at least it's sort of tempting based on the two examples to look at the module S mod I, but that isn't necessarily in here, and I'm currently not certain on how to reliably associate a module. So, without looking at particular examples, how to reliably associate a module in here to this thing here. So that you when you take the annihilator, you end up looking back at this thing here. But supposing we had such a module, so say we have such a module M, then we can take that and look at a matrix factorization, right? So say we have its free resolution. I guess this lives in there. So we look at this module M's free resolution. We can produce so we'll call this map P, this one E. We can produce a matrix factorization as follows. So given an S in Sn here, well, we have that f of S is in the kernel of E, right? Which is equal to the image of P, right? And that's just because M is an R module, so F must act trivially on M. Now, since the sequence is exact, there exists a unique T in here. So that's like this copy over here, such that Fs is equal to P of T, right? And we define a map Q as, well, we'll say that Q of S is equal to this unique T here, right? Okay, I might just sort of erase this top bit here. Okay, and then so the claim is that we'll claim S QP. Oh, sorry. I suppose it doesn't matter, but really it should be this way. Is matrix factorization. Well, by construction, we've got PQ is equal to F1. And then using the fact that P is a monomorphism, we can also show this also implies that QP is equal to F1. Okay, so it remains to show that Q is actually an S-linear map, right? So we can take S and S prime in Sn. And then in this case, we take also, we've got P of Q of S plus S prime. Well, that's just F times S plus F times S prime, which is just P of Q of S plus Q of S prime. And then again, we use the fact that P is a monomorphism, and we get what we want. We can see that it is compatible with addition, and then likewise we could show the same thing for scalar multiplication. Okay, so we can also show that this association sending a matrix factorization. So if we're talking about matrix factorization, maybe I should just go to a new board. So go to the third board now. So we can show that the association sending a matrix factorization to some module in KR, we can show that is, or we can upgrade that to a functor, right, by specifying how it works on morphisms, just using the universal property of co-kernels. And we've just shown, well, I haven't defined the functor, but if we had defined the functor, what we've just shown is that this functor is essentially surjective, but it doesn't induce an equivalence of categories. So, for example, if we take any m arising from a matrix factorization like so, then we can construct more free resolutions of m by just adding free summands. So I'll call this p and this e again. So, for example, we also have this thing. Okay, and the matrix factorizations that we can associate to each of these sequences are clearly not isomorphic. So, in other words, this functor from matrix factorizations to this category Kr is identifies non-isomorphic matrix factorizations. Now we can solve this issue by using a different category of morphisms for our matrix factorizations, which we'll define in the next, or we'll define shortly. And this, when we take this thing, it turns out that this category of matrix factorizations, which I will define soon, it's not equivalent to Kr, but to the quotient Kr mod R, right? So where we don't allow direct sums with R, I guess. Okay, and that proof uses sort of essentially the same ideas that we've been discussing here, and it's given. I've got a reference to where the proof is given in a textbook. In the case where Kr is the category of Cohen-Macaulay modules, but really the fact that the modules of Cohen-Macaulay isn't used. Cool. Were there any questions about that before we move on? Okay, cool. So we move to the fourth board now. Okay, so the answer is to look at the homotopy category of matrix factorizations. So we define a homotopy of a morphism of matrix factorizations in exactly the same way as for complexes. So I'll give that definition now. So a homotopy of some morphism alpha So these are all matrix factorizations of some common element. Say F is an odd S-linear map. Say H from X to Y, such that alpha is equal to dy H plus H dx. So usually this is drawn, at least I've seen it, drawn on the diagram like so. Where the triangles don't commute, but rather they sum to the relevant, the vertical map, the AI vertical map here, alpha I vertical map. We say two morphisms alpha and beta are homotopic if there exists a homotopy of alpha minus beta. Okay, and then we obtain the category of the homotopy category of linear factorizations by identifying homotopic morphisms, right? So if two linear factorizations are equivalent in the homotopy category, then we say that they're homotopy equivalent. And this is the case if and only if there exist morphisms, say, if this exists, so we say y is homotopy equivalent to x. So that's the case if and only if we have these morphisms alpha and beta, such that alpha beta is homotopic to 1, and so is beta alpha. Okay, and we denote this. So we denote the homotopy category of matrix factorizations. So this is of matrix factorizations now, not linear factorizations. So we'll denote that by HMF SF, right, for matrix factorizations of F, and then the subcategory of matrix factorizations which are homotopic to a matrix, which are homotopy equivalent to a matrix factorization of finite rank. We'll denote that by HMF SF. Okay. I'll go back to the first board. How are we doing for time? Okay, cool. Oops. Okay. So let's look at an example. Okay, so we've got our matrix factorization, or say a linear factorization XD. Then the linear factorization X, where we've direct summed another copy on of S here. So this is always homotopy equivalent to X, to the original matrix factorization here. Okay. So, and the way we get that is just by using the projection and inclusion maps. So, for example, if we have this, let's maybe make some space. So we can project down to the X component in each case. And then we can include back into the X component in each case as well. Better fill these in. Okay, and then we already have, well, that inclusion followed by projection is equal to 1. So it just remains to show that so now we just want to show that that projection followed by inclusion is oh no, what am I saying? Sorry, that inclusion followed by projection is homotopic to 1. Yeah, that's not too difficult to show. The homotopy is, I mean, yeah, maybe I won't go through it now just because we're sort of getting towards the end of the session.
Can you just write the map? Can you just write that down?
Oh yeah, okay, sure. Yeah, maybe. Yeah, I'll write it down on the next board. Cool. So that should be 1. Yep. So in each case, we have I pi minus 1. Oh, sorry. And then a homotopy that works is, well, we can take the direct sum of 0 with minus 1 here. So I should probably write these in. And then this can just be the 0 map. And that's gonna work as a homotopy there. Oh, actually, maybe it's maybe not. Oh no, sorry. Yeah, no, that's fine. Yeah, so that's going to work fine. Okay, so maybe the other thing I wanted to say. So so if we identify, so in the following lemma, I'm going to identify. Oh, sorry, were there any questions about that before I move on?
No, that's good. Thanks.
Cool. So in the following lemma, I'm going to identify a matrix factorization with a pair of matrices, just as we did at the start, and we'll say call the matrix factorization PQ reduced if either PQ is equal to the matrix factorization, the sort of trivial one, where the first is just 1 and the second is just F, or if P and Q have no unit entries. So that's just a definition. Then the statement of the lemma is every finite rank matrix factorization is equivalent in the homotopy category to reduced one. So that's sort of what this act of passing to the homotopy category is kind of doing concretely to the level to matrix factorizations. Cool. The only other thing I had left was to mention a theorem about matrix factorizations, and that is that the category, this homotopy category. So in the case that we're working in a polynomial ring over an algebraically closed field with the matrix factorizations of some element in that polynomial ring, that this homotopy category of matrix factorizations is the 0 category if and only if the coordinate ring of what we're factorizing is regular, right? So that's sort of saying that this homotopy category is only interesting if we've got some sort of critical points in our in the algebraic set associated to the thing that we're factorizing. So yeah, I just thought I'd mention that because it's interesting. Yeah, I'm not sure how to prove it though, so please don't ask. Cool, that's sort of all I had to say.
Yeah, thanks, Rohan. That was great. Any more questions?
So is a homotopy category still just a category? So the hom sets are sets, or are they more than that? Are they a homotopy space or a simplicial set or something?
Yeah, I suppose. Hang on. So you say more than a set, as in a set with more structure, or more stuff than a set, like a large
enriched category? Are the hom sets? Do they have, I don't know, something homotopical about them? Or are they...
Well, I'm not sure specifically, but I know it's like less. I guess maybe I should just say I don't know because that's the truth. Yeah.
They're just abelian groups.
That's interesting.
to go in the direction of enriched, I mean, to go in the direction you're asking for, you can consider just the Z2 graded space of maps before you take. So taking morphisms of matrix factorizations modulo homotopy is to take the zeroth cohomology of a Hom complex. That's true of sort of genuine complexes, and also true of matrix factorizations. And if you remember that Z2 graded Hom complex, then the category of matrix factorizations can be viewed as a category enriched over Z2 graded complexes. That's called a DG, differential graded category. And that can be turned into an infinity category, or any other gadget you like.
Yeah, that makes sense. I guess what is happening in my head is I'm kind of thinking, what are we doing when we pass to the homotopy category? I mean, the motivation here is fine, right? But to work up to homotopy makes sense in a way, but I thought maybe a goal was to enrich the category. We actually want these Hom sets to have a homotopical structure or something like that. It doesn't quite seem like that's the point.
Well, so when you look at it I mean, this isn't what you're saying, but if you want more motivation for why we pass to the homotopy category, if we look at it geometrically, whenever so this homotopy category is equivalent, if you look on the third board, it's still written up there, to this category KR mod R, right? Where we mod out by the module R, quotient out by the module R. And whenever like M is the direct sum of R plus some other stuff, then if you take the support of that, then you get the entire zero set VF, right? When we go through these steps and try and look at it as a subset of this. So if you mod out by that, then you get rid of these extra copies of R, and you get to see something else. Yeah.
Sorry to interrupt, guys. I'm going to head over to deprecation for Eleanor's session. Feel free to follow us when you're finished discussing, but don't let me interrupt you on that account. Rohan, I at least figured out on the boards over yonder where the SLT session was that the Annihilator is contained in the ideal generated by X plus Y. I didn't quite finish, but of your exercise, I was trying to do it.
Oh, yep, cool. Yeah.
Okay, but I'll see you guys in the next session or elsewhere. Thanks again, Rohan. That was great.
Yeah, no worries.
Thanks, Rohan. I think that's the end of our discussion. So that was really helpful.
Okay. Yeah, cool. I'll have some notes to send to that, and I'll head over to the next session as well.